Hello, a very good afternoon to all of you.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
Very good afternoon. So, as you can see, today our main focus of discussion will be unit number 12 and 13. And let us see that unit number 12 is basically about the solution procedure of method of variation of parameter for particular integral of differential equation, and unit 13 is method by using the differential operators. So we are going to begin our discussion from unit number 12. So let us move to the page number 77. So now look at the outline of this differential equation with variable coefficients. So here, this particular unit contains a method to find out the solution of using variation parameter method, and next we're going to discuss about the reduction of order. That means how we can reduce the order of a differential equation, and then we're going to solve. And finally, in third one, in 12.4 article, we're going to discuss about the Euler's method. That means how we can solve Euler's differential equation of second and higher orders. So now let us begin with the variation of parameter method. So now in variation of parameter method, so these methods are basically to find out the solution of complete integral of differential equation of non-homogeneous type. So in our last session, we have clearly discussed about the solution of homogeneous differential equation and solution of non-homogeneous differential equations. And as we know, when the differential equation is non-homogeneous type, we have two solutions. First one is YC, that is the general solution to the differential equation of homogeneous kind. And second one is YP, that is a particular solution, a particular integral of the non-homogeneous differential equation. So after combining these two results, we can find out the general solution or complete solution to the differential equation. So now let us move to the general procedure to discuss about the variation of parameter method using non-homogeneous differential equation. So as in your screen, as you can see in equation number 12, this is clearly a non-homogeneous differential equation with variable coefficients. So it is a differential equation of order 2. Look at the first term, it is y double dash. Second term is a1x into y dash. Third one is a2x into y equals to bx. So here, as bx is not equals to 0, so clearly this is a non-homogeneous second order linear differential equation. So now, to find out the solution of such kind of differential equation, we have to find its solution in two different stages or phases. In first phase, you have to find out the solution as or according to the corresponding homogeneous differential equation. That means we are treating the right hand side Vx equals to 0. So if Vx will be 0, if we substitute the value of Vx will be 0, then the differential equation will be converted to homogeneous differential equation. And its solution will be in the form of Yc. That is the general solution to equation number 13, and that will be represented in the form of C1y1 plus C2y2, as we have discussed earlier in the last session. Now, with the help of this particular expression, so with the help of this particular expression means this Yc, we are able to represent the particular solution in the form of Yp. So look at here in this equation number 15. The only difference is that from equation number 14, we are replacing the constants C1 and C2 by two unknown functions like u1x and u2x. That means in place of the constant c1, c2 in general solution of the differential equation, we are substituting functions of x, ux, u1x and u2x. So here the expression is like that u1 y1 plus u2 y2. So now the rest of the calculation procedure will be we have to calculate the derivative of this yp. If I want to calculate the derivative of yp with respect to x, that has been written in equation number 16. So here we have collect the derivative with respect to x, but we have collect the derivative of u1 u2 in first term, and in second bracket we are collecting the derivative of y1 and y2. So in this way we have to choose or we have to select or we have to write in the form of u1 dash u2 dash in a first bracket or in a particular term, and then second one must be in the form of y1 dash and y2 dash. So according to that one, now to find out the solution. So now our aim is that to find out the values of that u1 and u2 that was unknown to us according to the variation of parameter method. Because here we are choosing u1 and u2 are the two unknown functions as or in place of the constant c1 and c2. So that's why this is also known as variation of parameter method. So now here we have to take the first factor or the first bracket in equation number 16, that is u1 dash into y1 plus u2 dash into y2, that has been taken 0. So we call it as a first auxiliary condition. So when the first expression will be 0 in the right hand side in the bracket, then the equation will reduce to the very simple form. Then after reducing this equation in the form of 80, again we have another 4 terms. So look at that equation number 19, the solution procedure. So again in equation number 19, again we have to take one more auxiliary equation. We have to take it as 0. So after calculating the derivative of yp, and again we have to take the derivative of double derivative of yp. So these derivative are represented in equation number 18 and equation number 19. Now we are substituting the value of yp, first derivative of yp and second derivative of yt in the given differential equation. So after substituting all these value of yp, yp dash and yp double dash in the differential equation, we have a relation in equation number 20. That means the equation or differential equation will looks like in the form of equation number 20. Now, as we know that in this expression, y1 is the solution of the differential equation, and also y2 is the solution of the differential equation. So they will satisfy the differential equation. Now we are substituting these two values in the expression, equation number 20. So after substituting this value, we have again one more condition here. The equation will becomes e1 dash y1 dash plus u2 dash y2 dash equals to bx, and that is obtained from the equation number 220 after substituting these two particular conditions. So now we have a pair of equations in the form of u1 dash u2 dash and y1 dash u1 dash in the form of this pair of equations. Now we are going to solve this particular pair of equation in terms of u1 dash and u2 dash. So here we have used omega, that is capital W Wronskian, you can say Wronskian of y1 y2. That is the determinant of order 2 by 2. Here first row is the solution y1 y2 and second row is the first derivative of the solutions y1 dash and y2 dash. So that is the value of the Wronskian determinant. So basically this is the relation which will develop a complete formula to find out the solution of a differential equation using this variation of parameter method, and that has been written here in equation number 24. That means if we are going to integrate equation number 23 both sides with respect to x, then we will get equation number 24, because our aim is to find out the value of u1 and u2, because these two are the unknown function we have taken in place of the constant c1 and c2. So after substituting the value of u1 and u2 in the respective equation of yp that has been taken in the form of u1 y1 plus u2 y2. So here in place of u1 we are using the corresponding integral value, and again in place of u2 we are substituting the corresponding integral value. Then this equation number 25 is the concrete formula to find out the solution of a particular integral or solution that is known as particular integral of non-homogeneous differential equation. And later the following steps are given how we can find out the solution to the differential equation that has been discussed. So again, let us focus on these two terms. So here y1 and y2 in the solution of the particular integral, y1 and y2 are the solution of the homogeneous differential equation, whereas u1 is now under integration, that is minus dx into y2 divided by Wronskian determinant, the value of the Wronskian determinant, plus y2 into under integral, that is integration dx into y1x divided by Wronskian determinant w. So this particular formula is useful whenever we are going to solve a differential equation is non-homogeneous type. So now let us move to discuss about the solution of a non-homogeneous differential equation using this kind of variation parameter method. So now look at that example number 2. In example number 2, a differential equation is given, and the differential equation is second order linear non-homogeneous differential equation, and it has been defined over the interval 0 to pi by 2. So as we know, whenever we find a non-homogeneous differential equation, we have two solutions. First one is yc, and then we have to calculate the yp. So yp is the solution that is known as particular integral, and yc is known as general solution complete integral. So here now we are substituting the value of y equal to e to the power x, because that is the standard procedure to find out the solution of homogeneous differential equation. So after substituting y equal to e to the power mx in the differential equation, we will get an auxiliary equation in the form of m square plus 1 equals to 0, and we will get the value of m will be now here plus minus I, that means complex conjugate roots are there. Now after getting complex conjugate roots, we can now find out the solution in the form of y1, that is cos x, and y2 in the form of sin x. So now the complementary function is given by yc, or the solution to the differential equation or homogeneous differential equation. It will be c1 cos x plus c2 sin x. Now in the second step, we have to assign the value of yp, and here yp equals to u1 cos x plus u2 sin x. Now we are adopting the same procedure. We are first calculating the derivative of y2 with respect to x, and after calculating derivative with respect to x, look at the derivative of u1 and derivative of u2. These two terms will be taken as 0, and that is known as the first auxiliary condition. After taking these two term will be 0, then rest of the equation will be converted to, in this form, derivative of yp with respect to dx minus c1 sin x plus u2 cos x. Then again we are differentiating to find out the second derivative of the same. So after calculating first derivative, second derivative, we are substituting back these values in the differential equation. And again, after substituting back in the differential equation, we have to substitute the corresponding value of u1 and u2, because we know sin x and cos x are the solution to the differential equation. The corresponding value will be 0. So the differential equation will be looks like in the form of du1 by dx equal to minus tan x, du2 by dx equals to 1. So after solving these two relations, we will got the value of u1 and u2 in the form of ln cos x, and u2 equals to x. And now once we get the values of u1 and u2, we can now use these values in the expression of yp to get the particular integral of the non-homogeneous differential equation, and in place of u1 we are using here ln cos x, and y1 will be as usual same, plus u2 is x and y2 value is same sin x. So this expression is yp, means this is the particular solution of the non-homogeneous differential equation. So now finally we are going to combine these two solutions yc and yp to get the general solution of the differential equation of non-homogeneous type. So this is the simple procedure to find out the solution of non-homogeneous differential equation by using method of variation of parameter. So now let us move to the next pages to discuss about some other examples in the form of this concrete formula which was discussed in equation number 27. So that has been summarized in this theorem number 1. So this theorem number 1 is the result or the concrete formula of a non-homogeneous differential equation of order 2. So here we have taken the general form of the differential equation will be like this: a0 d square y by dx square plus a1 dy by dx plus a2 y equals to dx. So clearly in equation number 38 it is clearly a non-homogeneous second order linear differential equation. So if we are going to calculate the solution, or the particular integral will be here yp, and that will be represented in the form of minus y1x, and this particular integral is the value of u1x, and the second term will be plus y2 into this integral. The second integral will be the value of u2x. So here we have to memorize this formula to find out the value of u1 and u2 during the solution process to solve some questions or when we are solving some questions. So after getting the value of yp, then easily you can calculate the value of yc, that is the solution related to the homogeneous differential equation of the same differential equation. So here we are combining the yc and yp to get the final solution of the differential equation in non-homogeneous type. So this theorem number 1 gives us idea about the differential equation of second order. But again, we can see this idea or basic idea can be approached to the differential equation of higher order. Now, look at this differential equation here. This differential equation is of now nth order. Now that particular formula will also be useful in a differential equation of higher order. It may be 2 or 3 or 4. The idea or basic idea formula will be exactly same, but the number of solutions, that is y1, y2, y3, will be according to the order of the differential equation. So some more examples are given in example number 4. Here it is given a differential equation or non-homogeneous differential equation of order 3. And first the solution of homogeneous part will be here e to the power x, e to the power 2x, and e to the power 3x. Then we are using the solution of this one, that is u1 e to the power x plus u2 e to the power 2x plus u3 e to the power 3x. So again we are using the same kind of solution procedure by using the first auxiliary condition to find out the values of u1, u2, and u3, as we have already discussed earlier in this particular session. So please go through each and every examples to complete your understanding. Now let us move towards page number 89. Now if you have any question, then please ask me regarding this variation of parameter method. Otherwise we are moving to discuss the process of reduction of order of a differential equation. Have you any question, anyone, regarding this variation of parameter method? Okay, very good.
No,
So now let us move towards the reduction of order. That means sometimes we can also find out the solution of a differential equation by reducing the order of the differential equation. It may be of order 2 or order 3 or order 4. Now order can be reduced, and then we can apply any one of the procedure whichever discussed earlier to find out the solution of y3 and yp as well. So let us, so here an example is given. That means what is the basic idea, how we can approach to find out the solution of a differential equation by using reduction of order. But before we are going to discuss about that one, let us move to the general procedure, how generally we can reduce the order of a differential equation. So here the procedure has been discussed in this example is so let us move to page number 91. 91. So basically here procedure is that first we have to find a solution, that is y1. Once we get a solution y1, then the second solution can be get by substituting the value, that is y2 equals to, in the form of v into y1. The same procedure that has been discussed earlier in the form of variation of parameter method. So here look at the example number 7. For now, let us move to another example. Look at that example number 6. So here this is a differential equation given in the form of order 2, and it is already given that y1 equal to x is a solution of the corresponding homogeneous equation. That means one of its solution is known to us. It may be given along with the question. If it is not given, then we have to verify by taking some functions like x or 1 by x or x square or 1 by x square, or some simple functions like sin x or e to the power x. So if once we can find the solution of a differential equation of homogeneous type, then that can be used to find out the second solution in the form of y2. And the procedure is like that. So here we have to take a relation, and the relation is here written, that is y equal to x into vx. So here y equal to, we can say v into y1. So y means it is a second solution, y2 we may also take it as y2, but here it is taken y. The new solution will be the product of the first solution, that is x, and an unknown function, that is here taken vx, and that is known as a trial solution for the differential equation. So now we are calculating the first derivative, second derivative by using the product rule, and again we are substituting the value of y, y dash and y double dash in the differential equation. And after substituting the differential equation, we got a relation in equation number 66 in the form of double derivative of the unknown function v. Now clearly this is a linear differential equation in v dash. Look at carefully. This is a linear differential equation in v dash. Now, as it is a linear differential equation, we have to calculate its integrating factor. In the formula is e to the power integration of px and dx. So px is the coefficient of v dash here. So here the coefficient is 1 by x. So the integrating factor will be e to the power ln x, and here as we have another formula, e to the power ln x is equal to x. So we have got a
Hello,
the
sir.
yes.
पर यहाँ पे इंटीग्रेटिंग फैक्टर में जो e टू द पावर इंटीग्रेशन 1 बाय x dx लिया है वहाँ पे प्लस सी क्यों नहीं लिखे लास्ट में?
क्या नहीं लिखा है?
प्लस सी सर, एक कांस्टेंट डालते हैं ना सर जब इंटीग्रेशन करते हैं तो?
हाँ हाँ, नहीं यहाँ पे कांस्टेंट नहीं डालेंगे, कांस्टेंट हम लास्ट में डालेंगे। फाइनली व्हेनेवर कैलकुलेटिंग द फाइनल सॉल्यूशन ऑफ द डिफरेंशियल इक्वेशन वी आर यूजिंग देयर द आर्बिट्रेरी कांस्टेंट। यहाँ पे हम डालेंगे भी तो कुछ फर्क नहीं पड़ेगा, लेकिन व्हेन वी आर यूजिंग दैट पर्टिकुलर वैल्यू इन आवर कैलकुलेशन दैट विल बी क्रिएट डिफिकल्टी। क्लियर?
ठीक है सर। जी सर।
So that is the value of x here. So now after getting the integrating factor, the solution procedure will be same as to the linear differential equation. And here the solution of the differential equation in the form of 66 will be now, that is v dash into x on the left hand side. That will, as we know, the left hand side will be converted to the total differentiation form, and after integration it will be in the form of v dash x. So this is the solution of the differential linear differential equation in the form of v dash. So again, now after getting the solution in the form of v dash, this particular v dash is now again, this is the differential equation of first order. So now it can be solved by using direct integration, because in the right hand side there is the only variable x. So by using direct integration we can find out the value of v in terms of c1 ln x plus 4x to the power minus 1 by 2 plus c2. So this is the value of the unknown function v that has been taken as a trial solution in our calculation procedure. So basically, as we can see, the process is according to the reduction of order. First, we have taken a trial solution. First, we have taken a trial solution by choosing or by taking the unknown function v, and in this procedure we have calculated the value of unknown function v, and finally we are using that particular value to express in the solution of that y equal to x into v. So this is the trial solution, and we are again substituting back the value of v to get the general solution of the differential equation. So in this way, you can find out the solution of a differential equation by reducing its order, but condition is that a or one of the solution is given to us. Otherwise, we have to find out a solution by using fit and trial method. Now let us move to the next article, which is about the Euler's differential equation. That means the solution procedure of Euler's differential equation. First we focus how can we represent an Euler's differential equation, or how it looks like. Then we are going to discuss about the solution procedure of an Euler's differential equation. So we are moving towards that particular Euler's differential equation. So very first, in Euler's differential equations. Hello. So Euler's differential equation here. Some examples are given in equation number 67, 68, 69, 70. These are the examples of some Euler's differential equation. So in all these differential equation, it is very much common that
Clearly not audible, sir.
maybe your network is poor. So now look at carefully. Here the coefficient of the second order derivative of y, it is x square, and in the second one is also it is x square in the second and x cube in the third order. That means in Euler's differential equation the coefficient must be in the form of x square or x cube according to the order of the derivative of unknown function y. So here, as you can see, in the first term the coefficient is a0, but here we have multiplied a monomial, that is x to the power n, as this particular term contains nth derivative of y. And second one, a1 is the coefficient, but here that is a product of a1 and x to the power n minus 1, because here the order of the unknown function or the dependent variable y is n minus 1. So if a differential equation will be particularly in that form, then this kind of differential equations are known as Euler's differential equation. It may be of second order, fourth order, or nth order. And in these examples, one more equation, look at that equation number 70. This equation number 70 is not in the perfect form of Euler differential equation, but it can be converted in the form of Euler differential equation by substituting a value of capital X in place of 2x minus 1. Because if we substitute 2x minus 1 equals to capital X, then it will be our desired form of Euler's differential equation. So now let us see. So whatever the constant we have used here, a0, a1, a2, up to an, all the constant in the right hand side are the functions of x alone.
सर समझ में नहीं आया सर, एक बार फिर से रिपीट कीजिए ना इस पे।
कहाँ से बोले तो?
सर वो जो 2x माइनस 1 को आप लिए ना, ये क्या है x?
हाँ, इक्वेशन नंबर 70 जो आपका दिया हुआ है डिफरेंशियल इक्वेशन, that is not in the perfect form of Euler differential equation, but we can convert it if we substitute a variable capital X that is written here. We have to substitute the variable capital X in the form of 2x minus 1, because once we substitute in place of 2x minus 1, so that will be capital X cube, and here dq y by dx cube, and then in the second term it will be x into dy by dx. So particularly our desired form of the Euler-Cauchy differential equation. So constant may be any value, but the coefficient of dq y by dx cube must be in the form of x cube, or third degree of the variable x. So now whenever the differential equation is in the form of Euler-Cauchy form, then we can use the auxiliary equation. So here the process of calculation, so detailed derivation is given how we can find out the auxiliary equation of the differential equation in Euler-Cauchy differential equation. So here, as you know, in our previous calculation to solve a differential equation of homogeneous type, we are substituting e to the power mx to get the auxiliary equation. But here we have to substitute x equal to e to the power z, or we can say that z equal to ln x. So now let us see how we can find out the auxiliary equation of the same kind of differential equation in Euler-Cauchy form. So let us move to the general procedure of Euler-Cauchy differential equation. So let us see here in example number 11. So here it is an initial value problem of the differential equation of order 2. So here the equation is like that: 4x square y double dash plus y equal to 0, and that has been defined over the interval minus infinity to 0. And the conditions are also given at minus 1, that is y of minus 1 equal to 2 and y dash of minus 1 equals to 4. Now we are substituting. So clearly this differential equation not in the form of exactly Euler-Cauchy differential equation. But now we can substitute it to convert this type of equation into constant coefficient form. So here our method is to convert the differential equation by substituting a new variable in the form of constant coefficient form. So we have taken here t equals to minus a. Then dy by dx can be expressed in the form of chain rule, that is dy by dt into dt by dx. So now from this relation of t equals to minus x, we will calculate the value of dt or derivative with respect to x, and that will be here minus 1. So after using this value, the value of dy by dx will be minus dy by dt. Similarly, we are using the second order derivative of y with respect to x, and again we are using the chain rule to find out a relation in the form of t. So here it will be d square y by dt square, as you can see. Now this value of dy by dx and d square y by dx square will be now substitute in the differential equation along with this condition. So after substituting this condition, look at the differential equation. So now clearly this equation is converted to our Bezier form of Euler-Cauchy or Euler differential equation. So here the first term is 4t square d square y by dt square plus y equals to 0. So look at here, as we have d square y, that means second order derivative, and here we have t square, that means the Bezier form of Euler differential equation. Now after getting this kind of Euler differential equation, now we can use the substitution procedure or standard substitution procedure to find out its solution. So here the standard substitution procedure is that we have to substitute t equals to e to the power z, or we can write z equal to ln z. Now after substituting this relation in the differential equation, the differential equation will be converted to this particular form: 4 into d square y by dz square minus 4 into dy by dz plus y equals to 0. Now look at this particular differential equation in the form of z. So clearly this particular differential equation is a homogeneous differential equation with constant coefficients. So as we know, whenever we have a second order homogeneous differential equation with constant coefficient, we have auxiliar equation, and here the auxiliar equations will be 4m square minus 4m plus y equals to 0, because here we have to substitute again the same procedure or same substitution rule, that we have to substitute here y equals to e to the power mz. So after substituting y equal to e to the power mz, we will get this kind of auxiliary equation. And once we get auxiliary equation, it can be solved easily to find out the roots of this kind of auxiliary equation. And here roots are real and equal. So when we have a real and equal solution of auxiliary equation, our general solution will be here e to the power z by 2 plus all into c1 plus z into c2. So this is the standard form to get or to write the solution of a homogeneous differential equation with constant coefficients. And after getting the solution of general differential equation, we are substituting its initial condition, that is y1 equals to 2. Then we will get the value of c1 equals to 2, and from the second condition we will get the value of c2 equals to minus 5. And again we are substituting back these two values of c1 and c2 in the solution that was obtained earlier, and the solution will be looks like in the form of y equal to t to the power 1 by 2 all into 2 minus ln 5 into ln t. But clearly this particular expression is not the final solution to the differential equation, because the differential equation contains the variable or independent variable x, but here we have represent in the form of t. So again we have to substitute the value of t in the form of minus x. So again we are substituting back the value of t equals to minus x to get the final solution of the differential equation, that is the general solution of the differential equation. So here we have discussed the general procedure, how we can approach the solution of a Euler differential equation, whether it may be in the perfect form of Euler differential equation. If it is not in the Bezier form of Euler-Cauchy differential equation, then we have to substitute a standard function or standard variable to convert in the form of our Bezier Euler-Cauchy differential equation. So now let us move to discuss about the next one, and that is all about the equation reducible to Euler form. So as we have discussed in equation number 70, so here we can see how it can be converted in the form of our desired Euler-Cauchy differential equation. So here the same equation number 70 has been written. Now we have take here capital X equals to 2x minus 1. So this is the new variable we have taken here, capital X. But now we have to again represent the same equation in the new variable capital X. So that's why dy by dx, we have written here dy by dx because that has been used in the differential equation. So dy by dx can be written in the form of dy by d capital X and d capital X by d small x. So we are using here the chain rule because capital X is a function of small x. So that's why we cannot directly calculate the derivative of small y with respect to small x. So we are using here the chain rule. So again, according to the chain rule, look at the derivative of x, capital X, with respect to small x. This is 2. So here 2 is multiplied, 2 into dy by d capital X. In the same way, we are calculating the second derivative of d square dy by dx, that is d square y by dx square, and we will get here 4 into d square y by d capital X square. And again we are calculating the third time, the third order derivative of y, and it will be 8 dq y by d capital X cube. So we are calculating third order derivative because the differential equation contains third order derivative, first order derivative. So that's why we have to calculate the derivative up to third order. And now we are substituting all these values of first derivative, second derivative, and third derivative in the differential equation according to our requirement. The differential equation will be converted in the form of 89. So in this differential equation of 89 equation, we can easily see the first term is 8 into x cube, and here the order of the derivative is third order, that is dq y by dx cube. That means the Bezier form of Euler differential equation. So similarly, second term is x into dy by dx. So first order. So that's why the degree of the variable x is also first order or 1. So clearly, the expression is the Bezier form of Euler differential equation. So here, in this way, so this is only the conversion. That means how we can convert, or what is the approach we have to adapt to convert a differential equation that is not perfectly in the form of a differential equation. But again, let me to say, we cannot convert any differential equation that is not in the form of Euler-Cauchy differential equation to the desired form of differential equation. So there must be certain functions we have to substitute, otherwise we cannot convert each and every differential equation in the form of Euler-Cauchy differential equation. So same procedure has been adopted here in example number 12, and here we substitute 3x plus 2 equals to e to the power z. So look at here, we are not substituting here capital X or other functions, but here we have taken e to the power z. So once we have substitute this particular relation, again we can convert the differential equation in the form of a Bezier Euler-Cauchy differential equation, or it may be the differential equation of constant coefficients. So this is the procedure to convert a differential equation according to the Euler-Cauchy differential equation. So here in this particular unit, we have covered about the solution procedure of method of variation of parameter, and in this method of variation of parameter, we have used the value of u1 and u2 is a standard formula to find out the solution of y, that is the particular solution of the non-homogeneous differential equation. And then we have discussed about the reduction of order. That means how we can approach a differential equation to get its solution by reducing its order. So whenever there is a question, the procedure of reducing a order of a differential equation, we have to first know or find out one solution of the differential equation. It may be y1. So once we know one of these solution, then the second solution can be expressed as y1 into dx. And the solution procedure has been discussed earlier with some examples. Also, the general procedure has been discussed. Then finally, we'll discuss about the Euler differential equation. That means whenever a differential equation have variable coefficients with same as the power of order of that particular term, and that will be known as the Euler differential equation. So whenever there is a Euler differential equation, then we have to substitute, or there is a standard substitute procedure, and that is x equal to e to the power z to get the solution of that kind of differential equation. So after that one, we are moving towards the page number 160. So here in this particular unit, there is a method of differential operator. Now that is one of, yes, hello.
All right.
So here we are going to discuss about the method of differential operator. That means we can also use the differential operator as a standard tool to find out the solution of a differential equation of degree 2, order 2, or higher order derivative. So let us see how it can be approached, or how can we approach by using the differential operator. So here generally in this particular method we mainly use the notation capital D. So capital D is d by dx, differential operator with respect to x. So clearly you can say that d0y, d0y means d0, that means zeroth order derivative, that means the function will be remaining unchanged. Dy means first derivative, y dash, d square y means second derivative, y double dash. Similarly, dny means the nth derivative of the dependent variable y can be represented. So here some expressions are given: d to the power m into t to the power m equals to t to the power m plus n. So these are the standard operations or algebra of differential operator. So let us moving towards page number next page, that is 16. So how we can represent a differential equation using the differential operator. So look at the differential equation. So here the differential equation is like that: a0 into nth derivative of y, second term is a1 into n minus 1th derivative of y, and similarly clearly this is a non-homogeneous differential equation of order n. So here this nth order of y can be represented dny, n minus 1th order can be represented d to the power n minus y. So in this way, we can express the left-hand side of the expression in the form of the differential operator capital D, as we have mentioned earlier in this session. So now the left-hand side can be expressed, or we can here taking common the unknown function or the dependent variable y in the left-hand side. So by taking common y, the expression inside the parenthesis is an operator. So that operator can be expressed in the form of capital LD, and this particular operator is known as a polynomial differential operator of order n, because this LD is just look like a polynomial of degree n. So but here d to the power n means it is not a degree of d, but it is the nth order derivative of another function. So that's why this operator is known as polynomial differential operator of order n. So if we substitute back the same expression in the differential equation, the differential equation will be very simple and easy to express, and that is capital L dy equals to Px. So here LD is an operator that is operating on y and equals to dx. So meaning of the expression in equation number 4. Now some examples are given how we can approach the calculation procedure of this kind of operator in a differential equation. So now let us move towards the page number 119. In 119 page, some fundamental laws of the operations are given. So here the fundamental laws of this differential operators are given. Suppose we have a three L1, L2, L3 are the three polynomial differential operator, then this particular law or rule are satisfied by these three polynomial differential operator. That means they will satisfy the commutative law, associative law, and multiplication is distributive with respect to addition, and also multiplication is commutative, and also multiplication is associative. So these are the common and basic rules of these three types of or three polynomial differential operator. Again, this operator may be of any order, maybe all are same, maybe all are different, but they will satisfy all these five basic property and rule of the unknown function. So here we can also represent in the form of inverse. So as we know, d capital D equals to d by dx, that is the differentiation. If we represent d to the minus 1, that is the inverse of the differential operator, and inverse of the differential operator is nothing but the integration with respect to x. So that has been written here. So here inverse differential operator LD can be represent L to the power minus 1 in the form of D or 1 by LD. So that is inverse differential operator, and that will act as an integration over the unknown function u. So here again some algebra or calculation procedure are given, and also the theorems are summarized the calculation procedure of the homogeneous and non-homogeneous differential equations. So yeah, these are some algebra how we can use in differential operator and inverse differential operator. So here, look at this example number 1. So example number 1, we have here exactly third order derivative in the differential equation. There is a third order differential equation or third order non-homogeneous differential equation. And now, if we are using the differential operator capital D, so the term will be dq plus 2d square minus d minus the whole into y equals to e to the power 2x. So now look at this expression represent in the parenthesis that can be factorized in linear factor. That means here u is now, so after factorizing the expression in the form of linear factor, to find out its solution, we have to take the expression u is the last two factors along with y. That is taken as the standard function u. So here d minus 1 into u has been written, and that is equal to e to the power 2x. So now we are getting the solution by integrating both sides with respect to x, that is the solution of u now. Then similarly, we are calculating this. Similarly, we are adopting the same procedure to get the other value with respect to d plus 1 and with respect to d plus 2. So the process of calculation by using the differential operator to get the solution in the form of differential operator. So here a 1 by 1 factor we have utilized. So first we have used d plus 1, then d plus 2, then d minus 1 has been used to find out the solution of the differential equation in three different stages, and each stages we are calculating through the integration process. So here, So if you have any question, then please ask me. Otherwise, we are going to end the session.
No question, sir.
So please go through the examples which we have discussed or what are the text given in your textbook. If you have any doubt, then that will be discussed in our next session. So I would like to thanks all of you to join in the session. Thank you.
Okay. Thank you, sir.
Sir.
Thank you.